All right, so we've reached a point in the course where the amount of new syntax and new ways of programming is sort of winding down. What we're going to be starting to look at more is what we can do with programs and how we can improve the way we write programs. And some of that you started seeing in the last module on encapsulation. While I did introduce generators, really encapsulation is more of a concept and it's a way of programming. It's a discipline as opposed to syntax. In this module, we're really focusing, again, not so much on the syntax, but examining, what can make our actual programs better, regardless of the syntactical nature of it. So one of the big things that define the quality of a program and how good of a program is how fast it runs. Does it run quickly? And across all sorts of domains, speed in which a program can run is a big differentiator in terms of whether a user wants to work with your program. If you're writing a search engine, does the search results come back fast? Certainly accuracy is probably the most important thing in a program. If it doesn't return the right results, it doesn't matter how fast it gets it wrong. But after that, probably speed is one of the biggest considerations that we have. Now, realistically, in many situations, computers are so fast, your personal computer is so fast that worrying about speed is probably pointless. Um, if you're developing a large scale application that is going to be run, millions and millions of times, performance starts to become more of an issue. If you are looking at very, very large data sets, and that's very, very common in engineering and scientific domains, um, you might be thinking about running a program that's sort of number crunching for minutes or maybe even hours or days. When you start to get into programs like that, time actually starts to make a difference. If your program's runtime is an hour, well, if you can figure out a way to make that half the amount of time, that's a big savings. If your program only runs for 3 seconds, then shaving 1.5 seconds off the runtime probably isn't that big of a deal. Um, Likewise, if you're writing a program that maybe you're only going to run once or twice a week or once or twice ever, maybe runtime doesn't make much of a difference. But if you're running this program 15 times a day, actually that time starts to add up. So often the algorithm, the sequence of steps that we choose to solve the problem with, actually has a huge impact on the total runtime of your program. And that's what we're going to be looking at today. Not so much on the, how do we cut time or choose a better algorithm. That's a case by case type basis. But more importantly, how do we quantify it and how do we measure it and how do we sort of develop a little bit of a vocabulary about talking about runtime? And the term that computer scientists use instead of purely runtime generally is the term computational complexity. A program of a higher computational complexity is generally speaking going to have a larger runtime or a longer runtime than another program. So the computational complexity refers to the measure of how much work the CPU must do to arrive at a result. And we're going to refine this definition as we go here a little bit, but that's probably a little bit too simplistic. But one of the things that you probably that you must be prepared for is that often decreasing the computational complexity of a program, so decreasing the runtime simplistically, um, most of the time it ends up increasing the conceptual complexity. And what do I mean by conceptual complexity? It's harder to program. It's probably a more intricate set of steps. It's probably a less obvious set of steps. If you read the code, it's probably less clear 3 months later what you are actually doing than maybe a program of less computational complexity. However, generally, again, the payoff, significantly faster runtimes, is worth the programmer's time. Again, under the right circumstances, right? So if you're writing a program that you're only going to run once and it runs for 30 seconds, it's not worth spending an hour and a half making it run for 20 seconds instead. But for a lot of cases, your programs are run often or they're going to run a very long period of time, and it makes sense to spend a little extra time and develop a little bit more, maybe complicated program that can run faster. Okay, so how do we measure runtime? Um, how long does the algorithm on the left take to run? So if we look at this algorithm where it's got a function, we didn't really name this nicely, the function f, it starts with an answer of 1, and it's simply looping through each value starting at I, and calculating the sum of the successive values. So if I was to call f of 5, really what this function is doing is computing 5 plus 4 plus 3 plus 2 plus 1. So the question becomes, well, how long does this program take to run, and what does it depend on, right? Certainly, if I calculate f of 5, this is going to be a very, very small amount of time this program is going to take to run. But how do we really measure it? How do we quantify it? Well, first of all, it certainly is going to depend on the speed of the computer, right? If I run this function, it doesn't matter what number I pick for I. If I run this function on a computer that I buy today, and I run this function on a computer that I had 20 years ago, no question about it, right? The speed of the computer makes a difference. The newer computer most likely is going to be much faster, and such that the program will run far faster. I can also take this algorithm, which is just, remember, the sequence of steps. If I change this and ran this in C++ or any other programming language, all these programming languages also have while loops. They look a little different, but it's the same idea, right? They still have variables. So, if you were to see this code written in C++, you would not feel all that lost. It would look relatively the same. One aspect of the speed of this program is the actual speed that Python executes at. Right, so not all programming languages execute at the same speed, and that has to do with a lot of things, but largely, very early in the course, we talked about the way the Python interpreter is set up. So it takes Python code and on the fly generates binary code that then is run on the CPU. Python's an interpreted language, and there's overhead when you run the program. Every time you run the program, Python's converting your code into binary. Other languages, so for instance C++, when you're done writing the code, you compile it ahead of time into binary. And so every time you run the program, it's actually already in binary code. It runs far faster. And there's a lot of other reasons why C++ also runs faster than Python. So if I was to write this algorithm in the equivalent C++, it would absolutely run faster than writing the same algorithm in Python. That's certainly true. The third reason that we could, or the third thing that the runtime depends on, is actually the more interesting case. This function's overall runtime will vary depending on which value of I you pass into this function. Right? If I pass in f of, if I call f and I give it 3, well, this loop's going to go around 3 times. If I give it an I of 10 million, then this loop's going to go around 10 million times. That is a really, really big predictor of runtime, right? So the value of I essentially is governing the overall runtime of this program. So the first two reasons are true, but as a computer scientist, generally I'm using the language that I chose for a lot of different reasons, and I can't really easily change that. Sure, I could buy a faster computer, but as a computer scientist, I'm generally going to be more concerned with how does my algorithm behave for changing values of I. So, an individual operation, an individual step is going to always run faster on a faster CPU. So, of course, we could just say, hey, buy a faster machine if you want it to go faster. An individual operation in one language will always have different runtime than another. Okay, that's usually, by the way, much less of an impact than one might think. In some situations, it is such an impact that you really do need to choose a language based on that. Um, Frankly, that's fairly rare. As a programmer, the algorithm makes the difference to us. And by the way, a carefully crafted algorithm can generally have a much bigger of impact than all of the above. If we choose really carefully crafted algorithms, sometimes that we can overcome um, the cost of a slower machine or even a slower language. So in computer science, we don't talk about runtime in like seconds or milliseconds or nanoseconds. And the reason for that is everybody runs a program on a different machine and becomes sort of comparing apples to oranges. And in 10 years from now, nanoseconds might be too big of a time scale to measure things on. So it doesn't really make a lot of sense for us. But instead we measure steps, because this function that I have here, this is going to be the same set of steps today, tomorrow, 20 years from now, or 20 years ago. It's the same number of steps. Each individual step might take longer and shorter period of time, but if I measure in number of steps, that'll kind of capture the quality of the algorithm. So let's assume that if I is 1, right, it's coming in as 1. Well, then this loop is going to calculate, it's going to actually go around this loop once, right? If I is 1, answer gets set to 1. I less than or equal to 1, yes. Answer plus equals I, and I'll return the answer. The algorithm completes in 7 steps, right? So we've got 1 step here to assign answer. We've got 1 step over here to check whether I is greater than or equal to 1. We've got 2 steps here. Answer plus equals I is actually an addition and a assignment. It's 2 steps. It's a combined operator. Same thing down here. And then we return answer, and that's the next step. So what we want to do is come up, we saw that it was 7 actual steps if I was equal to 1, but more generally speaking, how can we calculate the number of steps based on whatever that value I, almost like as a function of I? And if we look carefully at this, there's always 2 steps, right? There's always a step that we initialize answer and we return answer. Those are always 2 steps. But the while loop itself consists of 7 individual steps. We have a comparison, and then we have 5 actual steps. We have a comparison, and then we have 2 operations, a plus and an assignment, and then another 2 operations, a subtraction and an assignment. So 1, 2, 3, 4, 5. So if we wanted to define the number of steps based on I or n, really it would be 2 plus 5 times whatever the input is. And so I'm calling it n or I. It doesn't really make a difference. First rule in measuring time, right? In terms of algorithm, if we think about as n varies, as n gets large, 100, 1,000, a million, no one cares about those 2 initialization steps. No one cares about the 2. The 2 plus 5n, comparing an algorithm that runs with 2 plus 5n operations to an algorithm that runs at 5n operations is silly. It's trivial. And the reason is because 2 is constant. It doesn't change with the number of inputs. And as 5 gets large, it's kind of drowned out. It's an insignificant part of the overall runtime. And from a practical standpoint, 2 operations cost you literally nothing in terms of real runtime. Right? And so we know that this function is going to be fast for n's less than a few million, in fact. So you'd have to get very, very high n's before you get really an appreciable difference in runtime. So the first rule here is that the constant plus the linear time, right? The time that's growing linear with n, the constant part generally gets thrown away and we don't really talk about it. In fact, we generally don't really even worry about the specific n, the specific constant. What we really classify this as is a linear algorithm. This algorithm takes longer to run, proportional in a linear manner, in a straight line, to n, or to the size of the input, or the number of iterations around. So I, or n, is essentially controlling this. So as I, or n, grows, right, the runtime of this behaves linearly. If it's 5, it's got a slope like this. If it was 1, it would have a shallower slope. If it was 100, it would be rising more quickly. Generally speaking, the actual slope, the 5, is not considered all that important either. The fact that it's linear is what makes the difference. All right, now, why is that? Well, intuitively we know that if something's running at 100 times n or 2 times n, hey, I'd prefer the 2 times n, and that's true. But probably we wouldn't prefer it enough to spend days trying to figure out a way to make it faster. And that's sort of, it's a relative comparison. Um, how do we make things really faster? So much faster that it's worth spending, lots and lots of times programming something. Well, I have a little bit of a trivial example. First of all, let's put a better name on this function. That f of I kind of seems a little weird. This function is actually computing the summation of n. And names go a long way, right? Because as soon as you start thinking about that, if you look up and you Google summation of n, if you don't already know the formula, there's actually a much better formula. Instead of looping through every single value and adding and accumulating a sum in answer, there's a straightforward answer of n times n plus 1 over 2. And here's the deal. No matter what n is, this algorithm grows linearly. If n is 1,000,000 or if n's 10, we're going to have a vastly different runtime. Over here, it doesn't make a difference whether n is 1 or n is 10 trillion. Right? If we can do the math, which we can, it's still an addition, a multiplication, and a division. There's 3 operations here. Either way, doesn't make a difference what n is, there's always 3 operations. This is called constant time, right? It does not make a difference what the input is, it still runs in the same amount of time. Constant time versus linear time is huge. That is a totally different ballpark. Even if something costs us, 1,000 operations, if it's constant and if it never grows, it's still better than linear, even if the linear is of 5n, right? Because as n gets very, very large, eventually the linear algorithm will take longer. And frankly, we don't care about how fast our program is for small inputs. We care about how fast our program is for large inputs. So it's not really worth considering the fact that, well, maybe a really slow constant speed is worse than a really quick linear. There's no such thing, right? We think about as n approaches infinity, what's better? There is no question that the constant time is far better than linear. And if you programmed your code this way, might not be quite as intuitive, but it's vastly, vastly better. That's a real simple solution. In fact, that's one of these easy solutions where there exists a better algorithm that's probably just as simple to program, right? This doesn't include a loop, it's pretty easy. Most situations aren't so nice. Most situations, in order to get that kind of an order of magnitude improvement, we got to do some more complicated things. So let's turn our attention to search, because this is a good example, and we're going to actually use this example later on in a later module when we cover search algorithms. I'm going to just talk about some of these things briefly right now, just to give you an idea of how to compare them. So I've got a typical search algorithm here that accepts a list L and is looking for a value X. So first of all, just as a side note, in Python, we can just say is X or if X in L, and it would work, right? So this is sort of a contrived example, but nevertheless, in other languages, we don't have that in operator. So if I want to find whether or not X is in L, I could loop and visit every single element E in the list L. And if it was the same, if it was a match for what we were looking for, I could return true. If I went through the entire list and I never found anything, I could return false. So we've got 2 cases here. We've got many cases, but we've got 2 general extremes. We might find a value right away, right? So if if X is 5 and 5 happens to be the first value in this list, we'll turn right away. That's sort of the happy case, the real, the perfect situation. Or we might never find a value, right? So if we're looking for 5 and 5's not in the list, if the list has a billion items in it, we have to go through this for loop a billion times until we realize, hey, 5's not in that list. Generally speaking, we're not always going to get the good case. We're not always going to get the bad case. So it's safe to say it's roughly half of an n, right? You're gonna go around this loop about half of n times. Because we generally don't care about the constant, we would say that this is a linear search. This is certainly a linear search. And the question is, well, can we get something that's nonlinear, right? Can we get something that's better? And it turns out that if we know something about the list, and that's a big if, and I'm going to get into this more when we cover searching, but if we know that the list is in order, we can come up with a very different method of searching that is going to be legitimately more complicated to program. It's going to be more complicated to understand, but it's going to behave in a much, much faster way. We're going to be able to find values far quicker. And the idea basically works the same way as looking up in an index or looking up in a dictionary. Given an ordered set of inputs, instead of starting at the very beginning and going one by one looking for a value, it's actually a lot smarter to just skip to the halfway point. Right? And once we're at the halfway point, decide, well, which half of this list or of this book should I continue my search in? Right? And I could repeat that, cutting the search space in half each time over and over again to find the value. So just kind of to sketch this binary search out. Let's say I'm searching for the value 28. Right? So I could go into this and I could cut this list roughly in half, right? And look at a particular value, right? So 15. So I'm gonna keep track of my comparisons, right? So I got a comparison at 15. If I know that this list is in order and I know that I'm searching for 28, I know something. As soon as I find 15, I know that all of these numbers, without even looking at them, can't contain the number 28. All right, so I've knocked out half the search space. Now notice how different that is from starting at the beginning. If I start at the beginning and I look at 2 and I know that that's not 28, the only value that I can say is definitely not 28 is the one I just looked at. But by skipping to the middle, I can definitively say every value to the left is not 28 because 28 would have to be to the right. Now I can take the rest of this list and split it in half again and look at the value. And again, when I see 24, I see 24 is less than 28. Well, everything to the left of 24 is knocked out. That's 2 comparisons, and I've knocked out 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Next operation, skip to the middle, 31. In this case, I don't need to look at the 42. Right? The 31 is bigger than 28. Therefore, no numbers to the right of 31 could be 28. And then finally, I only have one value left, and it is 28. And if it happened to be 27, I would have to assume that 28 is not there anymore. Right? So in this algorithm, this binary search algorithm, by cutting the list in half in successive orders, I'm able to find the value in 3 searches. Now, that's a very, very simple case. There are some carefully crafted cases. By the way, if I was searching for the number 2, binary search actually would be slightly slower than linear. The linear search, because the linear search gets lucky and finds it right away, where binary would have to skip to the end, to the halfway points. But overall, binary search behaves much, much better than linear. Linear would have cost me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comparisons. By cutting the search space in half each turn around the loop, instead of reducing it by 1, you can see pretty clearly that we're sort of charging towards this answer much faster. And it turns out if you run this program and you do a search of a list of 10 or a list of 100, 1,000, 10,000, binary search is probably pretty comparable in terms of overall runtime. Like you wouldn't notice the difference between, this number of iterations, because iterations are so fast that both of these programs would complete on the order of nanoseconds. But you notice at n equals 100, linear search is taking about 50 comparisons. Binary is going to be around 5.8. At 10,000 elements, we've got 5,000 comparisons. Binary search will still be able to find a value on average in about 12 and a half comparisons. This is called a log n because we're log base 2, meaning we're cutting it in half. How many times can we cut n in half? Log 2. All right, the log search or a log-based search is going to be dramatically faster as n gets larger. So we saw in our linear search that there was a factor, right? There's a factor. If we loop around, we had some number of operations. If we had a comparison to see whether we should return something, the search we could say would be b times n, where b was some number of steps in our loop that went around n times. The binary search is c times log n. C meaning some other number of steps per iteration. But the key here is that I'm not looping n times. I'm looping log n times. It turns out that it doesn't matter what B and C are. It makes absolutely no difference. It doesn't matter whether B is much, much smaller than C. As n gets large, the n and the log n are the things that we're really comparing. Log n is far, far faster than linear search. So we've got a great algorithm. And by the way, we'll cover the actual code for binary search when we look at searching algorithms in a future module. So don't be too concerned with how we code that right now. This big O notation, all right, this order, it's based on the idea of omega, but also some people think about order of magnitude or orders of magnitude. O1 is the symbol that we write when something's constant time. And by the way, it doesn't matter whether it always takes 5 operations or 1,000. We don't write O5, we just write O1, constant. Linear is when we need to actually visit every single value in an input. So we're gonna go around the loop, let's say, one more time for every additional input value, no matter what. Think about printing a list. There's no better way. We can't visit every number and print a list without visiting every number. So it's got to be linear. Log n is an improved value. Sometimes we'll have algorithms that are n times log n. Those are both fairly good. N squared, quadratic, that's typical when we have a loop within another loop. That can become very expensive. Generally, quadratic runtimes are problematic because as n grows, the number of iterations of our loop starts to really grow out of control. Lastly, the last class that's probably the most expensive is exponential. Algorithms that are exponential, so their runtime grows exponentially with the size of the input, are to be avoided if we can, because we can easily start to have algorithms that even the fastest machines can't complete in lifetimes. To give you an idea of the differences, I've plotted out number of operations is on the left, and the number of input elements. And so you can see for a really small number of input elements, all of these algorithms, constant time, log n, n log n, n squared, I even did factorial out here, they're all relatively the same. But as n starts to grow, you notice right off the bat we've got 3 of them: the factorial, the exponential, and the quadratic. The number of operations starts to skyrocket, right? And these are a very small number of elements, in fact. We can see that log n is extremely small. Constant is sort of embedded in here. As n gets very large, log n is climbing, constant is not climbing. Linear is still kind of near log n, but again, as n gets much larger, linear continues at a rate at a constant slope, where log n is sloping, is approaching a more constant slope. Huge differences between these algorithms and their counterparts over here. So what does all this mean? Um, Really, for multiple problems that we encounter, there's probably a number of different ways to solve the problem. There's multiple algorithms that exist that will get the right answer, right? So step one, becoming a programmer, is learning syntax, right? Step two is writing programs that produce correct answers. We're sort of moving into the third step now, where, yeah, we're going to write a program that is syntactically correct. And yes, we're going to get the right answer. But now we're going to try to figure out clever ways to make things run faster. And a lot of times the most obvious algorithm might run at linear or might run at n squared time. But there might be a non-obvious way. There might be a way that if we really think hard about something, if we really, we make some optimizations, we make some good assumptions, we can get things down to log n. We can get things down to constant time. And again, if your program is running for hours, or if your program is going to be run, 100 times a day, um, that effort to come up with a better algorithm is very, very likely to be worth it, worth your programming time. Sometimes, by the way, though, there are no ways to reduce complexity. And there's a whole field of computer science researching algorithms and classifying some algorithms that just simply cannot be done in any faster time than maybe even exponential. Those are called NP hard problems. So we need to not only be aware that there might be better algorithms out there for what we're doing, but we also need to be aware that sometimes we're developing an algorithm that there is no better way of doing it, and understand that are the ramifications. For large inputs, some of these algorithms that we come up with are not computationally feasible, and we need to deal with that. And there's those are all have to be dealt with on a case by case basis. So as we continue throughout the rest of this course, this is all something that we're going to try to start to talk about a little bit more. How do we do things faster? How do we maintain efficiency? And we're going to use this language of big O notation to sort of classify the difference between different algorithms and determine whether or not it's really worth comparing or improving the algorithms that we're using.